For 4.1, we're going to continue working with areas of parallelograms, and the key purpose that I want you to keep in mind here as we do this work today is that you can derive or come up with the formula for finding the area of a parallelogram by using what you know about the area of a rectangle. And we did the work on that in class, and we noticed the direct relationship between those two, so keep that in mind as you are working with your area of parallelograms. The area of a parallelogram is the product, which we know means multiplication, of its base and its height. And the formula we're going to use is going to be capital A for area, and then B times H, where, again, just getting to know these pieces, A means area, in this case, of a parallelogram, and B means the base, and the H means the height. And again, it's okay to put the B and the H right next to each other right now because they're both variables. If you wanted to put a multiplication sign in between there, you could put the dot, or you could use the parentheses, or you can do none of those for right now and you can just leave it like this until you start substituting some numbers in there. For example 1, when we're going to find areas of different parallelograms, this first one, letter A, says that it has a base of 12 meters and a height of 14 meters. So we're going to use that formula, area, which is capital A, equals B for base times H for height. And again, feel free to stick that multiplication sign if you want, but the base of this one is 12 meters. And we're not going to worry about putting meters in when we do the actual work. And the height is 14 meters. And now we're going to remember that we have to put some kind of a multiplication sign in. So use a dot or use parentheses, but show multiplication somehow. And then do your side math and figure out 12 times 14, whatever strategies you have for that. We know it's 168. And remember that meters have to be squared because all area uses square units, or you know it's also okay if you want to write it as square meters, that's fine too. For letter B on example 1, we're going to continue to use the same formula, area equals base times height, but this parallelogram is doing something a little bit different. It's almost like it's on its side. So we have to notice that the base here is actually 8.5 feet, and then the height is actually 4 feet. And the reason we can tell those apart is because remember that height is the one that's going to be going from a base, in this case this is a base here, and then this one could technically be considered a base, but they're probably the same length. And then it has to be perpendicular, which remember perpendicular would go something like this, and it would kind of make a right angle here, like this one does in the corner over here. And so that one is still our height, even though it's kind of tipped on its side. So when we go to fill this in, again, we know the properties of multiplication. We mean that even if we get that backwards and we put them in the wrong order, we're still going to get the same answer. But we do want to be able to determine the correct base and height. So 8.5 feet is our base, and 4 feet is our height. So we're going to substitute those in. And from working with the fractions and mixed numbers before, we need to remember that with a mixed number, before we do anything like multiply it, we need to turn it into an improper fraction by multiplying the denominator by the whole number. So 8 times 2 is 16. Then add the numerator, plus 1 is 17 halves. And then we can just turn that whole number into an improper fraction by putting it over a 1. And then just like we did with all our other fraction work, we're going to see if we can cross simplify. If I divide this one by 2 and divide this one by 2, then this number will become a 1 and this number will become a 2. And then I should check both ways before I cross, but I can't go any lower over there. So my new fractions are going to look like 17 over 1 times 2 over 1. And I don't have to do any flipping or moving or anything like that at this case. I just have to multiply across, and then 17 times 2 would give me 34 over 1, or you can just know that 34 is equal to 34 over 1 is equal to 34. And again, we're going to check our labels this time, and it looks like they're in feet. So we're going to label that as feet squared or square feet. For example 2, we're going to find the area of a parallelogram, this time using a grid, which looks like a coordinate plane here. And so one thing we're going to do, kind of like we did in our activity, is we're going to use the squares to count out and help find the area that way. When we start counting, we can see the base can be right here still. Those can be considered 2 units because even though this one is only a half square, we're not counting up right now, we're counting across, and it does cover that full square there and this full square here. And same thing over here. Even though there's a little bit of this next square colored in, it's not going across the base. So this one, we could consider the base to be 2 units. And I'll put a little B next to that as a reminder. And then the height this time gets a little tricky because, of course, we can't just go straight up from corner to corner the way it's situated. But we can remember that if we could draw a line from here to here, that we would start at either one of our corners. So this would work, but either of these up here would work too. And we're just trying to go from one edge to another, or one corner to another, straight up and down, and this is where the grid lines come in handy. So if I just start up at this top corner right up here and kind of follow that grid line all the way down until it's even with the, whoops, I'm a little bit off on that one, until it's even with this one right here, then it still makes a right angle, so we can still use that as our height, and then we would just count how many squares that was. So it's 1, 2, 3, 4, 5. So that gives us a height of 5 units. And this kind of happened in your on your own problem for example 1. It was the second on your own problem, and they kind of drew the height outside of the parallelogram. So it's important to know that that will happen sometimes, but that the distance is equal to what it would be in here. But because it's such a narrow parallelogram, it's just a little hard to draw it corner to corner right inside, so they do it outside sometimes too. But then your formula is exactly the same as it has been all along, which is area is equal to base times height, and then you just fill in there. Base we said was 2 units, height was 5 units, and then when you multiply them together you would get 10, and again, since there was no actual unit of measurement like centimeters or feet or inches, we just go ahead and put it as units squared, or square units would be fine too. For this on your own problem, I probably should have mentioned on the last screen too, I'm not expecting you to draw the grid by any means. You're certainly welcome to help yourself to graph paper from our classroom if that makes it easier to do this on graph paper. Otherwise, you could just draw the basic outline of the parallelogram and kind of approximately put in your measurements, and then of course to actually put the measurements in this one you're going to have to count them out. So you're going to have to count what the actual base would be and write in what that would be. For instance, I'll put a B where the base might be, but you would actually put the number that would go there. And then same thing over here with height. You can either go corner to corner on the outside like what we did, and then once you figure out what the actual height is right here, then you would put that number in, and then you would go through and do your work. The last example this time is a real-life application, and it says you make a photo prop for a school fair, and you cut a 10-inch square out of a parallelogram-shaped piece of wood. What is the area of the photo prop? So notice this is your parallelogram, and they give us a base and a height, and this piece is missing, so that's what we're going to focus on in this problem. Is we know we can find the area of the parallelogram, but then what do we do to take out this piece? Maybe I assume that's something where someone could put their face in for a picture or something like that. So let's see what we could do with that. So if we start by breaking the formula down by words, the area of the whole prop here is going to be the base times the height of the parallelogram, and then we are going to want to subtract the cutout there, subtract that cutout, which is the area of the square, And I accidentally wrote the formula in here, which is fine, but I should have put it in words first, is what I said. So area of the parallelogram, or of the wood, the prop, okay, is right here. And when we start to fill things in, there's one other little thing that we need to pay attention to here, which is that the units of the actual wood piece are in feet, but if you notice the cutout, that's in inches, and we need to make sure that we're using all the same units. So in this case, I think the easiest thing to do is to convert from feet here to inches. So remember that there are 12 inches in every foot, so if we multiply this by 12, that will give us inches, and if we multiply this by 12, that will give us inches. To go ahead and work with here. So 12 times 4 would give us our 48 inches, and then 8 times 12, again, do side math if you need to, but that would give us 96 inches. These don't have to be squared yet because we're just converting, but we're going to plug them in to the formulas down here, and then we'll deal with a final unit and what that should look like. So when we go to fill this in here again, when we are using the area and the base, we're going to remember to do the inches form right here. And then, so that's going to be, and then we're going to use this one right here. So we'll put in 96 times 48, or 48 times 96, doesn't really matter. And then we're going to subtract the area of the square, and this with the two arrows tells us, because of course squares all have equal sides, that each of the sides is 10 inches. And because that whole gap right there is the amount we're trying to take out, then we would do 10 times 10, or 10 to the second power as the area of the square. So it doesn't really matter to me if you write it as 10 times 10 or 10 to the second power. And then you go through and you do your multiplication of 96 times 48, and then 10 times 10, which we know is 100, and then you'll subtract to come up with your final area here. So if I went ahead and did the side math, and you can and should already have done that, but 96 times 48 gives you 4,608, and then subtract from that the 100 that you get from multiplying 10 times 10 together, and then when you go to actually subtract that, whoops, this equal sign just got off a little bit. Down here, 4,608 minus 100 would give us 4,508, and because we converted everything into inches now, these are in inches, this was in inches, these were in inches, so our final unit of measurement will be inches, and it will still be square inches as our final answer, because we were looking for the area of this whole piece of wood, which we found by taking out that tiny little square there and finding the rest of the area up here. So our final answer is 4,508 inches squared. For this last on your own problem, when it says find the area of the shaded region, remember that you're going to be noticing here that there is a piece that is not shaded, and so you're going to have to take that piece out, just like we did in example 3. So the area of the shaded region is going to be all of this kind of yellow space, and you've got a base and a height, but you don't want to have that area included, so you can use your problem solving and use example 3 as a model for how to take that out, and the answer is coming up in a minute.